topics today are drainage patterns, stream channels, and the different types of stream deposits, or remember this word, alluvial deposits. So if you were to take a topographic map, which is a fun thing to do if you ever get the chance, and get a piece of tracing paper and just trace the blue lines or the streams or the rivers on the topographic map, you'll see that depending on where the topographic map is, what area it covers, you will have different types of patterns. And those patterns form as a result of whatever type of bedrock that the river is moving through, or they could be forming in response to the topography of the surface. So the ones that I'm going to talk about today are dendritic, trellis, rectangular, radial, and my favorite, the deranged drainage pattern. Here they are in cartoon form. So the dendritic pattern looks like the branching of a tree. Trellis pattern, I'll explain what that is when I get to the map showing trellis, but mainly in areas like the ridge and valley, which is a subsection of the Appalachian Mountains, where you have linear valleys divided by linear ridges, hence the name ridge and valley. So we'll talk about those. Then radial patterns, parallel we won't worry about because it's a derivative of a dendritic. Rectangular I will show you, annular we won't worry about, and the deranged drainage pattern. So this is a dendritic drainage pattern. It's like the branching of a tree. And dendritic drainage patterns develop in areas where the bedrock is uniform, parallel usually, so the river is able to cut down uniformly in all areas. So we have a dendritic drainage pattern. And this again shows these blue lines are superimposed upon the streams in this area, and you see that it is a dendritic pattern. Then this is a trellis. So the headwaters show up at the tops of the mountains. These would be the mountains. This is the valley here. And these tributaries then move into the main stem of the stream running through the valley. It's kind of like a trellis, like a garden trellis, if you will. They're kind of at right angles to each other. So that's a trellis pattern. Then this is a rectangular pattern. Rectangular patterns show up in areas where the jointing patterns in the bedrock are kind of at right angles to each other. The jointing patterns, remember, all rocks will have their own jointing patterns. Some of them are more linear than others. So there you can see how uniform they are. And then from an aerial view in an area that is vegetated, you can see how angular and linear they are. So they're following the jointing patterns of the bedrock. The stream is following the jointing patterns of the bedrock. And then this one is a isolated mountain, could be a volcanic cone, but you see how from the top of the mountain, the water has flowed down from the top of the mountain in this radial pattern, which makes sense. Water is going to flow from high elevations to low elevations and down all sides of the mountain. So radial pattern. Then a deranged drainage pattern is one that really has no apparent pattern. Usually in swampy areas or areas that have been glaciated, where you have a big ice sheet that moved through and there's still surface groundwater close to the surface. So the streams will just appear out of nowhere and then disappear into the ground with no rhyme or reason. And there are lots of little lakes. I couldn't find a really good topographic map to show this other than this one. Here's some swampy area, so you have a stream flowing in the swamp, out of the swamp, or into the swamp, and then it disappears. and you might have more of these all over the place. So just no pattern at all. And the types of channels, there are really only three major types. They're straight, they're meandering, and they're braided. So let's look at straight first. No stream channel is totally straight because Mother Nature is not uniform. There are differences in rock, there are differences in the speed that the water is moving, so they'll make a difference as to whether it's going to be eroding or whether it's going to be depositing, and that will change the shape of the river channel. So there's no truly straight stream channel. If you ever see a truly straight stream channel, it's man-made. It's either a concrete line channel or some sort of man-made feature. But they can occur over short distances. The stream can be fairly straight over short distances, usually near the headwaters of the stream in the mountains. And the classic shape is a V-shaped valley. The stream cuts down uniformly. In these headwaters, the main force is directed down. So downward. I swear, I hate this. I need one of those pens. Say the arrow went up. No, it didn't. Let's try that again. The force is directed downward. The erosive force is directed downward. So we get these nice, let me see if I can change this over here. These nice, no, I can't. These nice V-shaped valleys. Anytime you see a V-shaped valley, you know that a stream did the work. The stream eroded it. If you see a valley like that, a U-shaped valley, it was a glacier that did it. The glacier scoured all sides of the valley. Think of the Yosemite Valley if you've ever seen that. That's a classic U-shaped valley. Glacier eroded. But V-shaped valleys are from streams eroding. Then a meandering stream is a stream that winds back and forth, back and forth. Let me just mess this up even more, like this. Woo, woo, woo. Swooping bends. And a braided channel is one that's all over the place. It's numerous channels. Because the stream is carrying so much material that one channel won't do it. You get deposits of debris or alluvium that's built up that the stream has dumped, and the channels will cut around it. So let's look at these in a little bit more detail. This is a straight channel, but obviously not. If you look down here, look how windy that is. And that sets up the difference in the speed of the water. And the speed of the water will mean that if it's moving faster, it's going to be eroding more. If it's moving slower, then sediments will be dumped out. So this sets the stage for what comes next as the stream reaches lower elevations or as it matures and it's able to cut back into these valley sides. But there is a classic theory. I wouldn't say theory. There's a classic explanation in the world of geography about how streams develop. And one of them is, well, it starts out as V-shaped, and then over time, you get just a very flat area. There would be the stream. And you get wide floodplains over time. So given enough time, this stream could cut through those mountains, erode them down to what is called a peneplain, which is a flatter surface. And then when the stream is doing more erosion than anything else, this is where we're going to find some nick points. And there's our waterfall. If you remember, a waterfall is a nick point, but given enough time, the running water will erode the nick points away. So we get that nice concave longitudinal profile. There's Niagara Falls again. Here's a Nick Point, famous Nick Point in California, Bernie Falls State Park. If you haven't been there, you got to go. Go at a time where there's a high flow. The waterfall there is just incredibly beautiful. Then there are meandering streams. Meandering streams have these big, as I said before, these big sinuous curves. Meandering streams develop in lower elevations where the gradient is low. Erosion is concentrated on the sides of the channel, on certain sides of the channel. Water will flow more rapidly on the outside of a bend. So let me go back to this, and we look at the bends here. So this as I said before, this sets the stage for what happens later on in the life of the river. The river on the outside of a bend will be moving faster, so it tends to erode. On the inside of the bend, it will slow down, so it will tend to deposit material. So on the outside of a bend, we get a feature that's called a cut bank, because the bank is being cut into by the river because erosion is taking place. On the inside of the bend, the water will slow down. And when the water slows down, it's not capable of carrying all the sediment that it has in it. So it will begin to be deposited out. So I don't know why I'm bothering with this, because I have a diagram of it a little bit later here, but just so I can show you just how bad I am with this pen. So this would be the inside of the bend here, right here. So we would tend to get a point bar here. This over here is going to be the outside of the bend, so we would get a cut bank here. And that sets the stage for movement, because if things are being deposited over here, like sandbars or gravel bars, then that means that the river is being pushed this way. Here, deposits, the river is being pushed this way. So in this way, the river will make a very wide floodplain, and the floodplain is that flat area on the sides of river. Whoops. On the side, forget it. On the sides of rivers, where when the river is at flood stage, that area will be covered by water. All right, so here we go. Let me see if I can get another. I know you all are tired of hearing me. Hopefully you get a laugh out of what's going on here, because I'm so bad at using these. Let's just use the laser pointer. So here's a cut bank. That's the inside of the bend. And again, the reason that we get this is because the river the water is moving faster here on the outside of the bend. So it will cut, it will erode. No river is ever uniform across its width. There will be different depths to the river, and that means the water will be moving at different speeds. So this is the inside of the bend, and we have a point bar that has developed there. So here's your typical cut bank. This is not good because there's a road right here, and the next few floods could occur and the road could be undercut, and it would fail as a result of being undercut. Then this is what can happen. This house was built on a cut bank. Don't build your house on a cut bank. The river flooded and it undercut the house, and now it's unlivable. There's a little point bar right there. So this is a river in Alaska, and you see all along the length of the river, we have point bars, cut banks. Here's a big point bar right here. Here's a cut bank, and you see that all the way down the length of the river. Then you can imagine what happens at flood stage. Water comes just in turbulent flow down this river, do you think that that water is going to say, hey, yeah, I'm going to make this big bend right here? No, it doesn't. It's going to find a shortcut for itself. So it'll cut a new channel to connect to the other part of the channel. And it leaves behind these big bends. Those big bends are called oxbow lakes. And over time, the water in the oxbow lake can evaporate, and then we end up with meander scars. You see the making of one of those right here. Here's the oxbow lake, and here's where everything is drying out. The ground is drying out, so you've got some vegetation growing there. So that's going to be a meander scar. And you can see these things. They're very obvious on topographic maps. They're very obvious from satellite images. You can see where the river has been over time based on where the oxbow lakes are or where the meander scars are. Here's another view. There's an oxbow lake right there. Here's another one. So you can see how that river has been all over the place. So that's the entire floodplain of the river. And then this is a special type of meander. It's called an entrenched meander. These are the world famous goosenecks of the San Juan River. So you might think, well, did that river do all the cutting down? Partially, but not all of it. It had some help because this is on the Colorado Plateau, and the Colorado Plateau is uplifting. It has some of the fastest tectonic uplift in the country. So the river has had some help. As it's been cutting down, these rocks have been uplifted. And you can imagine, well, there, if the river ever gets high enough to cut through all that, then that would be like a little island that's been left behind, and there would be an oxbow lake around it. Then a braided stream. Braided streams happen where the stream varies in the amount of sediment that it's carrying, and that's usually on a seasonal basis. So in areas where you have streams that originate at glaciers, glaciers in the wintertime are frozen. So there's not a lot of flow that's going to come out. In springtime, when the glacier starts melting, remember a glacier is just a dirty bulldozer. It's just scoured out everything around it. So they're all sizes of sediments that are in the ice. Well, when that ice starts melting, then the stream starts flowing, and it's got an excess amount of sediment that it's carrying. So it can't possibly carry it all, so it begins to deposit some of the sediments out as these sandbars or gravel bars or boulder bars, whatever they happen to be in the river. And then there's more water coming, so the water just finds its way around these sediment dumps in the river, and you get all these streams that are braided in appearance, and that's why they're called braided streams. And here are some examples of these. These are both in Alaska, and you see all of the sediment that has been deposited by the stream, and all these different channels that are cutting around these deposits. Here's a braided stream in a tropical area. This was in Costa Rica, and there had been major floods there. So these rivers were carrying all of these deposits, and the channel was just having to braid itself around those deposits. There's a point bar right there. There'd be a cut bank over here. And here's some more braided streams. Again, these are in glaciated areas. Look at all the gravel bars here. Look at this one, it's all over the place. Multiple channels have been cut. Well, okay, what about stream deposits or alluvial deposits or alluvium? Streams will deposit sediment when the velocity of the stream is no longer capable of carrying that sediment. So the velocity decreases, its ability to carry material decreases, and the material settles out. Where might that happen? Well, we know that on channel edges it can happen where we get point bars. On valley floors it can happen, lower elevation, low gradient, so when a river reaches a valley floor, the material is going to come out. Deltas, like the Sacramento-San Joaquin Delta, and at mountain fronts and in desert regions, this is very obvious, where we have these streams that are rolling out of these high mountains, not a lot of vegetation to hold the flow of the water back. So when it hits the lower gradient area below, the speed of the water diminishes and we get deposits that show up at these mountain fronts. So we'll look at we've already seen point bars, then floodplains, alluvial fans. These are the fan-shaped deposits of sand, silt, and gravel deposited on a valley floor where a stream exits a steep mountain. Again, they're kind of like deltas, except they're in desert regions. Deltas are deposits that are formed when a stream flows into an ocean or into a lake. So here we go. This is a river in England. I could have chosen another one, but I like this one because it shows all this wide floodplain here. It also shows that there's not a lot of development in the floodplain, so somebody has been wise here. It's major farming area. Here's a cut bank. That's probably not so smart there, but sometimes you have no other choice because here's a road here. So there's the cut bank. Point bar would be here. And then this is a satellite view of an alluvial fan. Here are the mountains. There's a stream coming down. Look how it's braided itself. And then it hits this flat area out here, and the sediment is deposited out into this perfect fan shape. The heavier stuff would be here. The lighter stuff would be out in here, the sands, the silts, and the clays. And these can make pretty fertile areas, so if you can get water on them. So what they do is they irrigate, and that's what you're looking at here. Anytime you see that's perfectly straight, angular, rectangular, or square patterns, you know that there's some human activity involved here. Alluvial fans make really good aquifers because it's sand and gravel. And in the Middle East, what they do, we think of wells here. Our wells are vertical wells. Let me grab this pen again, see if I can actually do this. No, I can't. Our wells are vertical. What they do here is they poke pipes horizontally back to tap into the aquifer, and then water comes out. And that's what they use to irrigate the crops with. This is the bad water alluvial fan in Death Valley. You see this road built around it that washes out all the time, especially during the monsoon season in the summertime. But look at that. There's hardly any vegetation here. Look how steep those mountains are. So you can imagine you get these big thunderstorms, the water rolls out of here, and then it hits this flat area out here. So all the material will begin to settle out. Again, the heavier stuff would be up here. So boulders, cobbles, pebbles. And then as you get out here, you would have the silts and the clays that would be settling out. And then these are deltas in a glacial lake. This is in Alaska. So here's the water coming through, and there's the deposits of material in the lake. Here's another one. This is in Wyoming. And you see that nice delta shape. The color of the glacial water, you can always recognize that it's glacial water because it has this milky blue color to it. And that's because of the rocks that have been ground up so fine that we call it, can I even try this here? Rock flour. F-L-O-U-R, because it's so powdery. So when sunlight hits this material, it just gives it this kind of bluish color. I should say it gives it that milky blue color. And then this is the Mississippi River Delta. The Mississippi River Delta is a weird one. It's called the Bird's Foot Delta because there are all these distributary channels associated with it. It has moved over the past million years. It's moved back and forth as the river would carry sediment in. The sediment would build up. The river would have to change its path. And that's what's happened over this long period of time to give it that bird's foot appearance. Also, you see how there's not a whole lot of sediment coming out here. And that is because of a damming upriver. So a lot of the sediment has been cut off. So there are all sorts of environmental problems here related to gas and oil drilling, water extraction, the fact that the river has been so artificially changed. So this is New Orleans right here. And you can see what a precarious position New Orleans is in. This is Lake Pontchartrain. This is the Gulf of Mexico out here, and this is the Mississippi River. So it's surrounded by water. And we learned what a precarious position New Orleans is in after Hurricane Katrina, but we also learned what a precarious position Sacramento is in after Katrina, because the levees started being inspected, and it turned out that the levees weren't giving the protection that everybody thought that they were. So there was this massive effort to rebuild the levees, not only here in New Orleans, but also in the Sacramento area. We are an area surrounded by water too. We're in a bowl, we're in a depression surrounded by water, just like New Orleans is. So the Mississippi River, because the Corps of Engineers has done so much with building of levees and dams and locks and weirs and structures to keep it on its path, that's one of the reasons that we have such a lack of sediments down here. And it looks just like just this main stem that's flowing out into the Gulf of Mexico here. So the Mississippi River does not want to flow this way. The Mississippi River has found a more efficient way of getting to the Gulf of Mexico, but we can't let it do that because New Orleans is a port city. There are probably trillions of dollars, billions and billions of dollars of material that get exported out here from the docks and that are imported in. So if you left New Orleans high and dry, so to speak, there's no telling what the economic damage would be. So we have to keep it flowing toward New Orleans. What it really wants to do is way north of here. It's found a better way to get to the Gulf of Mexico. And that river there is called the Atchafalaya. So the Mississippi River really wants to do this. That means that the little town down here called Morgan City would be the New Orleans. Well, we can't have that. There's no infrastructure or anything that's needed for that. So we call the Corps of Engineers, and they build what's called the old river structure here. This is a system of locks, it's a system of dams, of weirs, and what happens is they have to let a percentage of the Mississippi flow into the Atchafalaya. Otherwise, this whole river would be flowing this way. So they have to let a certain percentage of it flow, but the bulk of it is directed into the channel here to keep it flowing, to keep it going toward New Orleans. There have been times when this whole structure was almost flooded over. There are times when they have to blow up levees in order to save New Orleans, in order to keep it from flooding, or in order for upstream flooding not to overcome this whole structure down here. It's all for the greater good, I suppose. And then this, of course, is your typical delta shape. This is the Nile River Delta. The Nile River flows north, and there was a dam that was built here, probably in the 60s, maybe early 60s, late 50s, and that's a lake behind it. So sediment is being cut off to this delta here, and if you just take a look at this picture, you see that only place where you see green is along the riverbanks and also on this delta. So this is kind of the life's blood. This is where a lot of most of the farming takes place, and it's shrinking as a result of the sediment being blocked here behind the dam. So that's problematic. That's one of the problematic things with building dams. All right, so I think that's enough for right now. We'll pick up with floods next time. See you later.